Now, in order to find the amount of work done, the amount of energy supplied to charge up, charge up this inductor to achieve the maximum current in the inductor, we consider first the I versus T graph, and we see that the EMF is equal to negative L times di dt. The slope being, and let me notate that so we're sure we understand it. The slope is di dt, and the inductance is negative L, and that's the EMF, which is the the voltage. So negative L times the slope. We know that the EMF is negative L times di dt, so the EMF is negative L times this slope, the inductance times this slope. And you can think about visually determining how much work it takes to get from here to here. At each point, we're going to have to multiply the slope by the negative L to get the EMF or the voltage, and then we got to multiply that by the current. So we're taking negative L times the slope times this quantity on the vertical axis. And you think about how you could visually do that, knowing that this function is exponential. This negative L times slope is actually going to be proportional to this distance here. And so we're basically multiplying this distance times the slope at this point, and then times the inductance. Any case, power is equal to current times voltage, or in this case, current times the EMF that we're using to achieve the current. So that knowing that the power then is I times EMF, EMF being negative L times di dt, we have an obvious expression for the power, and work is going to be the integral of power with respect to time, since power is the time rate at which work is done. So power times dt just formally is going to cancel out that dt. It's not really a cancellation, and you should think about what it really is, but that's going to leave us with Li di. Now I have a negative sign in there, and I'm kind of suppressing some of these negative signs. This would be the work that we have to do to achieve this difference, and that's going to be equal and opposite to the work done by the system. So it's going to be Li times di dt times dt, which is just Li di. So we're integrating Li di from 0 to I max. And that integral is trivial. You're going to get I squared over 2 out of this, and you multiply that by L, and then you evaluate it from 0 to I max, and you have 1/2 L times I max squared. Now this is the energy stored in the inductor, because we put this work into the circuit, and we put this work into the inductor, not just into the circuit, but this is the work that's gone into the inductor, and that work is there stored within the field of the inductor. So I can say this is the work stored by the magnetic field of the inductor. Now I'm going to write something down off screen. So I've written just energy stored in the field of the inductor, and the magnetic field of the inductor is 1/2 L times I max squared. Now there's another thing we can actually do here that I couldn't write on the board because of the poor resolution, and I'll do that in just a second and put that on here. There's another really important idea analogous to the energy stored in a capacitor, which you recall was 1/2 Q over C. And that's not right. It's 1/2 CQ squared. But you can get that by integrating the current with the voltage for capacitor. Okay, we've done the same thing here, integrating current with respect to voltage, essentially, as we did here. Now that we know the energy stored in the capacitor, and think of the example we started with, the coil, cross-sectional area 3 square meters, length 10 centimeters, giving it a volume of 30 cubic centimeters, or 3 times 10 to the -5 cubic meters. We could take that volume, cross-sectional area times length, and divide that into the energy to find the energy per unit volume stored in this capacitor. Now, this expression can be written in terms of the magnetic field B. The L, well, this can be written in terms of the magnetic field B of the charged capacitor. So we're going to be able to take the expression we get for energy per unit of volume and express it in terms of the magnetic field B, so that we then know energy per unit volume for a given magnetic field. And that's a kind of a significant thing that we definitely want to be able to do and maybe apply in certain conditions.